chapter 3 today on the prime numbers. So we've worked through all the material. We've done a lot of these end of chapter exercises in the tutorial last week, and then in the tutorial last week, and I did some in the lecture last week also. And we finished off by looking at, so this last section, this established results and conjectures concerning primes. This isn't examinable material or anything. It's just here out of interest. It's just looking at some of the, some of the topics that are studied in number theory, some of the more advanced topics, and some of these famous unsolved problems or unproved conjectures, okay? And among them, which we talked a little bit about last time, was the twin primes conjecture. And this conjecture says that infinitely often you will find prime numbers that are just 2 apart. So some prime number, and then the one 2 after it is also a prime number, okay? The conjecture says that this will happen infinitely often. Now, such prime pairs, have been found in large ranges of integers. So, there are large twin prime pairs known, but an infinite number of them. Although there are, I think a lot of people would believe that it is true. Now, we discussed last time that some recent progress that's been made towards this problem. And I think they can now prove that there are infinitely many pairs of primes that are at most 246 apart. Okay? So infinitely often you will find a pair of prime numbers in a range of integers that's 246 integers wide. 246 consecutive integers. Infinitely often you will find prime. Now, that the topics needed to argue that and to prove that are beyond the scope of this course. But we can prove a related result. So the twin prime conjecture says that infinitely often primes occur as close as possible together. And you can't have 2 consecutive numbers being prime because one of them will be even, okay? But you can have them 2 apart. That's what the conjecture says. Infinitely often they occur as close as they can. A related result we'll prove, and which I left you with last time, was looking at the flip side of that, saying that as well as prime numbers, the conjecture is that they occur as close as possible to each other infinitely often. But also we can say that there are arbitrarily large gaps between the primes. So when you go out in the sequence of integers, you come across large gaps between prime numbers, okay? So large runs of composite numbers. Now what we can prove now is that those runs of composite numbers are you can find them arbitrarily long, okay? It's the first assessment for the course is to get through the door successfully. Well done. So if somebody says, well, find me a gap of 1,000,000 between primes, or find me a run somewhere in the integers where there's 1,000,000 consecutive composite numbers, so that we can know for definite that there are no prime numbers in that sequence of 1,000,000 consecutive integers. Or somebody wants a run of 10 million consecutive integers, none of which are prime. That we can prove now, okay? So this is what we're going to do now to finish off this chapter. And this is the problem I left you with last week, and I left you with some kind of advice towards it. So in relation to the twin prime conjecture, we will show how to find arbitrarily long runs of consecutive composite integers. So this is like the flip side to the twin prime conjecture in a way. That says that infinitely often you can find primes nestling as close as possible together. Well, we can also show that there are also arbitrarily large runs of integers in which there are no primes, so that kind of forces the primes to be far apart. Okay. Now, this isn't hard to prove. This can be proved just with the methods we've developed so far. So the key ingredients in this proof are just the definition of prime, the definition of divisibility, really, and the notion of a factorial. Factorial numbers or factorial integers. So remember that n factorial is this number n times n minus 1 times n minus 2, and so on. So it's the product of all the integers between n and 1. Now what we're trying to do is trying to show that there are long runs of composite numbers. Factorials are numbers which, well, this certainly isn't a prime factorization. Lots of these numbers less than n will be prime, perhaps. But it is a view of a number which has lots and lots of factors. Yeah. So every number, including n, every number from n down is a divisor of n factorial. So it's got a rich composite structure, if you like, or rich and easily understandable in a way set of factors. Everything from n down, and we can exploit this to prove this result, to find arbitrarily long runs of consecutive composite integers. Well, how can I build a run of consecutive composite numbers using the factorial? Well, consider the numbers that begin from n factorial. So n factorial plus 1, n factorial plus 2, n factorial plus 3. Think of them all the way to n factorial plus n. I mean, what do you observe about these numbers? Well, there's a few odd ones to get rid of that don't fit a pattern. N factorial has lots of factors for sure. N factorial plus 1, well, we're not so sure about that. In general, you know, for large n, n factorial will certainly be an even number because it'll have a factor of 2 in it. So n factorial plus 1 will be an odd number. And yeah, maybe it's prime, or, I mean, it's probably not prime, but because most numbers are composite in a sense, but it could well be a prime. So, you know, we're unsure about that. But what about n factorial plus 2? Is that prime? No? Who said no? Why isn't it prime? Yeah, so like 2 is a factor of n factorial and 2 is a factor of 2. So 2, this whole thing will be divisible by 2. And is n factorial plus 3 prime? Why? It's got a factor of 3, because n factorial has a factor of 3. And 3 also divides 3. So yeah. So you can see the pattern, yeah? The next one, n factorial plus 4 is divisible by 4. N factorial plus 5 is divisible by 5. All the way up. As far as n will divide n factorial plus n. Okay? So we're using, I guess we could have, to rigorously justify this, we're using the result about divisibility of linear combinations. 2 divides n factorial, it also divides 2, so it will divide their sum. 3 divides n factorial, it also divides 3, so it will divide the sum. So this number here is a bit funny. We don't know about that. Maybe that's a prime number, maybe not. But these numbers, we can say are definitely not prime. They're definitely composite. And they're consecutive. Whatever n factorial plus 2 is, this is plus 3, plus 4, plus 5, and so on. Now, how many of them have you got? Well, we don't quite have n. We've got, how many of them do we have? We've got n minus 1. So this is a run of n minus 1 consecutive integers. But, you know, that's more or less the proof. So like, well, I guess if somebody throws a number in front of you, where's a run of, e.g., find a run of 1 million consecutive composite numbers. So a million integers, one after the other, none of which we know, such that we know for definite that none of them are prime. Well, this run begins, or such a run begins, with, now if we want them a million long, we have to form the factorial of 10 to the 6 plus 1. Because when you use an n factorial, you get a run of n minus 1 consecutive integers. If I want 10 to the power 6 consecutive integers, I need to take the factorial of this. And the run begins at this number plus 2. So this number is, for definite, a composite number, because the factorial has a 2 in it, and here's another 2. And the one after it, plus 3, one after it, plus 4, all the way up to plus a million, plus 10, sorry, plus 1,000,001, plus 10 to the power 6 plus 1. All those numbers will be consecutive. All those numbers will be composite. So that's the first number in the list, and the last number in the list is 10 to the 6 plus 1 itself. So we know, we've proved for sure that there are no primes in that list of numbers. Now that's a huge number. Factorial of 1 million is quite big. There could well be a run of consecutive composite numbers before that. We're certainly not claiming that this is the first time you get a gap of 1 million between prime numbers. It could have occurred before, but we're able to prove, that there are certainly no primes in this list. So none of these are primes. So that's like a companion result to the twin prime conjecture. The twin prime says the prime numbers infinitely often, they will occur as close as possible together. But this says that you also have arbitrarily large gaps between the prime numbers as well. Okay, is that okay? Any queries about that? Or what's interesting that this result can be proved relatively extremely easy. We've studied number theory for a few weeks and we can prove this. But the twin prime conjecture has resisted proof for many hundreds of years. and it's got an extreme amount of tension in the last couple of years due to the recent progress that's been made with it, but it's still, you know, it still is unproven. It's still a conjecture. Okay. Okay, any further points about that? Okay. And you can say a little bit more. Not only is this a list of 1 million consecutive numbers, none of which are prime, but such gaps occur infinitely often. If you take any factorial larger than this one, beginning with that number plus 2, there'll be another run of 1 million consecutive composite numbers. Yeah. As long as you start off with a factorial at least this size, so equally well, you can put into this bracket here, you can put in any number larger than 10 to the 6 plus 1. And then this list plus 2, plus 3, plus 4, plus 1,000,001, that will still be a list of numbers, 1 million numbers, none of which are prime numbers. Okay, but it's a different list. Yeah.
Is that the only form to get that many amount of random divided by different forms?
Well, it's the only form that I know of right now, standing in front of you. I wouldn't claim it's the only way to. I wouldn't say it's the only way to establish a run of consecutive integer numbers. But you can see how it all fits together. If you're talking about, if you want a list of consecutive numbers, you're talking about some start point plus 1, start point plus 2, start point plus 3, etc. So you're adding on consecutive integers. Well, very natural number to consider like that is the factorial, which is the product of a similar, list of numbers. So, once you see the argument and once you see it laid out like that, you say, oh yeah, it's obvious, use the factorial in that. But I don't know of another way to establish that result at the moment. I wouldn't claim that there isn't. But I suspect any way of proving it would, any way of giving it a direct proof like this, a constructive proof. This is a very nice example of a constructive proof. So someone says, well, where's the list of 1 million consecutive composites? Well, you take the input, 1 million, and that feeds into the proof of it. And it's a very definite construction based on the request for a list of 1 million numbers. As opposed to proving it in some mad convoluted way that says, well, there must exist somewhere a list of 1 million consecutive primes, but the proof doesn't actually tell you where it is or tell you how to find the start of the list or anything. It would be a purely existence proof. Those tend to be based on much more theoretical matters, whereas this is based on, confronting the thing head on. Yeah. Okay. Okay, so that's where we're going to leave chapter 3 for the moment. Unless there's any final questions or queries or anything so would like me to clarify from the chapter? Yeah? So would the one, so we know definite this is a composite number. What about the one after it? That's what you're asking. The one after it, I don't know. Is this number even or odd? Well, this number is even. This number is odd. Oh, well, actually. See, the factorial has to be even, so there's a 2 in it. This number is even plus 1, so this is odd. So the next one would be odd. Even plus odd. The one after. No, sorry. This number is odd because it's even plus odd. So the next one is even. So no, the next one is composite as well. But the one after that, we're unsure of. The one after that is an odd number, and who's to say? It'll be plus 3. Yeah, I don't know. It's hard to, So when you're looking at number theory, you're looking at these prime numbers. Sometimes you can prove things related to the prime numbers, such as here, and sometimes it's just a big kind of shrug of the shoulders and say, well, I don't know. I mean, for whatever that particular number is, you can test it. Just get the computer to test it, and tell you whether it's prime or not. But theoretically, I don't know. Theoretically, I'd say there probably isn't much you can say about it. Sometimes it'll be prime, sometimes it won't be. Based on different inputs than 10 to the power 6, yeah. Okay. So let's go back to the notes and let's begin chapter 4. So chapter 4 is on congruences. Now, congruences and modular arithmetic. Now, I know you've already been using this a lot in the cryptography half of the unit, and indeed you probably aware of and seen work with modular arithmetic before. But we do introduce it again now, and we do give a rigorous kind of treatment of the definition of it and some basic properties of it. And in future chapter, I think if looking up to chapter 6, speed up to chapter 6, Euler quotient function. Yeah, in chapter 6, we're going to tackle this general problem of solving polynomial congruences. So solving equations like this, where f is some polynomial function, but you're looking for solutions x, not of f of x equal to 0, famous, important class of problems to find the roots of polynomials. But in this number theory setting, we'll be looking to find the zeros of f modulo some other integer m. Okay, so that's kind of what we're building towards in chapter 6. So chapter 5 introduces the notion of modular arithmetic itself, starting off with the first definition. Okay. So we introduce this formally via this idea of a congruence relation. Okay. So a relation, we're going to introduce a new relation amongst integers. So formally, a relation is some kind of a statement that takes two inputs. So we're going to speak of A being congruent to B or not being congruent to B modulo some other number n. So it takes two inputs, A and B. So for any A and B, the statement is either true or it's not. So it's a relation. It's a rule for forming a logical statement, something which is either true or false. So you think of basic relations about. There's the important relation of equality, x equals y. It's either true or not. Various orderings, greater than or less than. X is greater than y. Could be true, could be false. Yeah, but they're relations. They're rules for constructing statements, as opposed to like a function, which is a rule to construct another quantity based on two input quantities. So here's the congruence relation. It's congruence modulo an integer n. So we're dealing with a strictly positive integer n. N is called a modulus, and we say that A is congruent to B modulo n. What that means is that n divides the difference. So n divides A minus B. And the notation we use, so we use this three-line notation, which is meant to be reminiscent of an equal sign, but it's not equal, so it's got 3 lines. So this says A is congruent to B modulo n. And if A was not congruent to B, then you just put a line through it, as you would a line through an equal sign to write not equals. So two things are congruent modulo n if and only if n divides their difference. Now, is this some completely new idea, which is unfamiliar to us? Well, no. I mean, it's readily understandable, and indeed, if you compare it with the thing we've already looked at, which was the integer division with remainder process, so you can take any integer and divide it by another one. It might go in evenly, or you might be left with the small remainder, smaller than the thing you divided by. Well, that's intimately connected with this congruence relation. So we can prove straight away this theorem here that says A will be congruent to B if and only if, so A is congruent to B modulo n, if and only if when you divide A and B by n, you get the same remainder. That's the point. We're saying that two integers A and B are related, they're congruent modulo n, if they both produce the same small remainder when you divide them by n. So we're classifying together, or we're grouping together all of the integers that produce the same remainder when divided by n. Okay. So for like a very quick example, e.g. if your modulus n is 7, and if A is equal to 3, well then certainly 3 is going to be congruent to 10 mod 7. 3 will be congruent to 17 modulo 7. Okay, because when you divide 10 by 7, and you divide 17 by 7, you always get a remainder of 3. And you can go in the kind of negative direction as well. Minus 4 will be congruent to, or sorry, 3 will be congruent to minus 4 modulo 7. 3 will also be congruent to minus 11 modulo 7. So when you divide those numbers, minus 4 and minus 11 by 7, you get a remainder of 3 as well. Remember, when you're doing the integer division with remainder process, the remainders that come out of them are always non-negative, greater than or equal to 0, and strictly less than the number you divided by. But, of course, 3 is not congruent to 11 modulo 7, because 11 produces a remainder of 4, which is not the same as the remainder of 3. Okay. So, as I say, you've been using this with Andy up to now, so we'll take it that people are familiar with it in a practical sense. Now, is there much required to prove this statement? Well, not really a whole lot. So it's an if and only if, so there'll be two directions to prove. First of all, we can set up notation. If you're going to divide A by n and B by n, we'll use Q1 R1 for the quotient and remainder for A, and Q2 R2 for the quotient and remainder for B. So these two remainders, R1 and R2, are both non-negative and strictly less than n. Now, if we are assuming, so we start off proving it's an if and only if. So we'll start off by assuming that A is congruent to B modulo n. So what that means is that n divides the difference. So let's talk in terms of the divisions. If n divides the difference A minus B, then that's going to mean that n divides Q1 minus Q2 times n and R1 minus R2. Now, n clearly divides this part because it has a factor of n sitting there. So if n divides the sum, and it also divides the first term in the sum, that means it has to divide the second one as well. Okay? Because you can write this second one, this bracket R1 minus R2, you can write that as well, all of this right-hand side will be some multiple of n. So you can write it as that multiple of n minus this multiple of n. So because n divides the sum and n divides the first part, it must divide the second part. So we get that n divides R1 minus R2. But how could that be? How can n divide R1 minus R2? Because R1 and R2 are both strictly less than n. They're both non-negative, and they're both strictly less than n. So they're both between 0 and n. So their difference has to live somewhere in the interval bounded strictly below by minus n and strictly above by plus n. Somewhere in there is the difference R1 minus R2, and there's only one multiple of n in that interval, namely 0. Okay, because it doesn't stretch as far as n and it doesn't stretch as far as minus n. The only multiple of of n that's in there is 0. So therefore, R1 minus R2 must be 0. So R1 is equal to R2 as required. They both produce the same, A and B both produce the same remainder when divided by n. Conversely, going in the other direction, because remember the theorem is an if and only if, we now suppose that the remainders produced by A and B are the same. Well, if the remainders are the same, then when you look at the difference, A minus B, the remainders will cancel, and you'll just be left with Q1 minus Q2 times n. And that is clearly, patently divisible by n, because it's some integer multiplied by n. So you can see it's divisible by n. So n divides A minus B as required. Well, so n divides A minus B, so that means A is congruent to B modulo n. Okay. So far from being something new, congruence is really just a way of saying two numbers are congruent if they produce the same remainder when you divide them by the modulus. Okay. So it's not really a whole new concept. Now, there's a theory behind relations. These are examples of so-called binary relations. Relations that take two inputs, so the A and the B. So congruence modulo n is a binary relation. It's a different one for every modulus n, but any one of these is a so-called binary or two-place relation. Now, a very important set of these are the equivalence relations. I mean, the most important binary relation is the relation of equality. Two things are the same object or not. And that's very important in mathematics, obviously. And equality has a lot of strong properties. To say things are equal is you're saying, you're saying an awful lot. But there are three important properties of equality: reflexivity, symmetry, and transitivity. But they occur for lots of other relations as well, and in particular for this one that we're looking at now. Okay. So when a relation satisfies these three properties, it's called an equivalence relation. You think of it as saying that the relation, it acts a lot like equality. It isn't the equality relation. You can have different things that are equivalent. So we have different integers that are congruent to each other, modulo n. But in a lot of ways, it acts quite like the equality relation. So what are these properties? Well, when you're presenting it theoretically like this or abstractly like this, we use the symbol tilde. So this is a tilde symbol. This is used to denote the relation. So this is like playing the role of equals, if you like. So x equals x, x equals y implies y equals x, and so on. But we don't use equals because we want to talk about, make it general, talk about other relations. So reflexivity is the property that every object x is equivalent to itself. Symmetry is the property that if x is equivalent to y, that means y is equivalent to x. Okay. Now, there are lots of examples of relations for which that isn't true. For instance, the relation of greater than. X can be greater than y, and if it's strictly greater than, that means that y isn't strictly greater than x. So you don't always have symmetry in relations, but for equivalence relations you do. Okay, so an equivalence relation has to be symmetric, that x is equivalent to y. That has to imply that y is equivalent to x. And thirdly, there's the property of transitivity. And this means that the equivalence, the relation kind of travels through intermediates. Because what transitivity is formally is that if x is equivalent to y and also y is equivalent to z, then the equivalence kind of travels through y, and it must mean that x is equivalent to z. If x is similar to y, or x is equivalent to y, or y is similar to z, it must mean that x itself is equivalent to z. Okay? So those are the three properties of being an equivalence relation. An equivalence relation is a relation which satisfies these. And when you have an equivalence relation, the terminology equivalence class, the equivalence class of an object X, and it's written square brackets X, that refers to the set where you gather together everything that's equivalent to X. You put it all in one pot, one set, which is the equivalence class of X, square brackets X. So that formally it consists of every Y from whatever the domain is, such that Y is equivalent to X. Okay? And these sets, these equivalence classes, are special in that they form a partition of the domain. And what's a partition of the domain? Well, there's a quick sketch for a partition of X. It's just a very general this kind of sketch. Any way you can split a large set up into a number of subsets, looking roughly like that, is called a partition. Now, okay, well that's just a very vague sketch on paper. It's not formally a definition of everything, but the two properties suggested by this sketch is that everything in the domain X is somewhere in one of these cells. So every element of the set X belongs in one of these cells that I've indicated here. So the cells or subsets cover the set X. And secondly, the other thing that's suggested is there's no overlapping going on. So two different cells are completely disjoint. Okay? So there's no object which is simultaneously in two of the cells. Any object is either in one of the cells or in the other one. Now you might think, well, what if it's on the border? What's on the fence? But, well, there is no border or fence in this sense. We're dealing with discrete sets, just kind of sets of points. So everything will be either in one set or the other. So that's just the image to have in your mind. But the formal statement of those properties is that a partition is of a set X is any family P of subsets. So the P would be the collection of all those subsets I sketched across X. And the two properties is that P, the set of subsets, must cover X. So if you take the union of all the sets S in the family of subsets, all the sets S in the partition, when you take their union, you get back the whole domain X. And secondly, the subsets are disjoint. So if you reached into the collection P and it took out two subsets, they have to be disjoint. Either you just took the same one out twice, or they're completely different, or their intersection is the empty set. Okay? So if you're holding a set S from the partition in this hand and a set S from the partition in this hand, either they're actually the same set or they're completely disjoint. There's no partial overlapping or partial intersections going on. So, okay, we've gone to the trouble of, or first of all, any queries about those definitions? So it's basically just a load of terminology. Equivalence relations, equivalence classes, and partitions. And the theoretical connection between them is that any equivalence relation, when you gather everything together into the equivalence classes, the set of equivalence classes will be a partition of the set. And partitions of sets are very useful things to have. It splits the whole domain up into a collection of subsets. So coming back to connecting with more concrete ideas, connecting back to this idea of congruence, we can prove fairly easily that congruence is an equivalence relation. Okay? And so congruence is reflexive, symmetric, and transitive. Okay? Now, congruence is defined using the divisibility relation that we introduced at the beginning of the course. So A and B are congruent modulo n if and only if n divides the difference. So all these properties of congruence, because congruence is really just a certain statement about divisibility, all these properties are coming from the properties we've already established for divisibility. So you can see we can deal with all three of them: reflexivity, symmetry, and transitivity. We can deal with all three of them in just this short paragraph. So let's see how we do it. Well, first of all, we want to prove reflexivity. So we want to prove that every integer is congruent to itself, modulo n. Well, we know that if we take a modulus n, we know that n divides 0. Every integer divides 0. That's one of the very first things we proved in the course. Everything divides 0. So in particular, n divides a minus a. But that means that a is congruent to a. Remember, the definition of, the thing on the left is congruent to the thing on the right. The definition is that n divides the difference of the two. If we know n divides 0, we know n divides a minus a. So that means a will be congruent to a modulo n. That's true for any a, so it says that congruence is reflexive. Next, symmetry. Well, so we have to assume that a is congruent to b, and then we want to prove that b is congruent to a. Well, if a is congruent to b, that means n divides the difference a minus b. But by an earlier property, and it's one of the initial properties of divisibility we looked at, if n divides some number, it also divides the negative of that number. Okay? But the negative of a minus b is exactly b minus a. So if n is dividing b minus a, that means b is congruent to a modulo n, according to the definition. So congruence is symmetric. Lastly, thirdly, maybe the hardest one to prove, or the one you have to be a little bit creative about, is to prove transitivity. So here we'll assume that a is congruent to b modulo n and b is congruent to c. And we want to prove that a is congruent to c. Well, you just interpret both of these assumptions. If a is congruent to b, it means n divides the difference a minus b. And if b is congruent to c, it means n divides the difference b minus c. And we want to reach a conclusion that a is congruent to c. So we want to prove that n divides a minus c. But that follows because a minus c is just the sum of these two quantities, a minus b plus b minus c. And we know that n divides this and n divides this. So when you add them together, n will divide the sum. So we get that n divides the difference a minus c, so therefore a is congruent to c modulo n. So we know that we now know that congruence modulo n is an equivalence relation for any integer n. So that means we can talk of the equivalence classes. Now the equivalence classes, they're not really called equivalence classes, they're called congruence classes. When we're talking about this relation, we talk about the congruence class of an integer. Or other terms that are used are, sorry, that's misspelt there, it's called residue class, or the residue, the collection of residues. Sorry, that word should be residue, not reside. So the congruence class, or the residue class of an integer, consists of all those other integers that are congruent to a modulo n. Okay? And when we're studying the integers modulo some modulus n, we often talk about the standard set of representatives, 0, 1, 2, up to n minus 1. Those are the standard representatives of the congruence classes, modulo n. Every integer is congruent to one of these modulo n. Because these are all the possible remainders you can get when you divide a number by n. Okay? So normally it makes most sense to study the integers modulo n by studying this set of residues. So those are sometimes called the standard set of residues or complete set of residues modulo n. Okay. So I'll be seeing you again tomorrow, won't we? Yeah, it's an odd week. So we'll continue with this tomorrow. There's some initial exercises to look at in the meantime, though. So I'll see you next time.